Okay. Okay. All right, it looks like we got quite a few people, so I think I'll get going. Yeah, let me grab a water. Okay, so I guess first of all, I should ask, are there any questions from the homework or from the reading? Okay. Well, so we did the background material last time, kind of the math preliminaries. And excuse me. Today we're going to start in on the programming languages aspect. So this is the material from chapter 3, starting with chapter 3. And I think I asked you to read up to page 38. And I don't know, it may be a little heavy sledding for you to puzzle it through, but let's get started so that you have more tools to understand the reading. So one thing I'm discovering is it's just unbearable putting these slides together. I feel like I'm have to retype the entire book. And then I try to do it in the morning before this, and it's just like this panic. Like I'm panicked up until the moment I turn this on, and I'm still like, trying to get enough stuff on the slides that we can carry through with a lecture. But so what he uses here, and he makes a nice he does have some nice references in this book where he refers to things and says, he cites certain work. So the language that we're looking at is BIMS, and it's a very small programming language. And here's a description of the entire language. And the thing that I was thinking of when I said he makes some nice you know, references that maybe stuff that I didn't maybe know was that I know that this particular language is a standard language for used for trying for describing semantics of imperative style programming languages. And so if you remember from your reading, in imperative style, you have kind of like all the commands, which are these kinds of things, like an assignment statement or a sequencing statement or if then else or a while. All of them, the assignment statement is the one that really gets work done. And what is it doing? It's modifying an external. We oftentimes call it store in the semantics, but you can just think of it as like memory. You couldn't run your program without memory. And so that's what we mean by imperative, is that the language is a sequence of instructions on how to modify memory so that the end of the program, someplace in memory, and you have to say where it is, contains the answer that you're interested in. You know, you'll notice there's no print statement here, but if you think of the memory as holding the kind of the state of the computation, you start out with maybe an empty memory, and at the end, whatever stored in memory is your answer. And his citation here was to a paper by Jacopini and Bohm, where they proved in 1966 that this language is Turing complete. So now, what does that mean? I mean, you may hear this before. Does anyone know what it means to be Turing complete? Can anyone volunteer a guess? No. All right. Maybe I need to find out. Can you hear me? Raise your hand if you can hear me. Okay, good. You can hear me. All right, good. Okay, so Turing complete. I mean, this is a pretty interesting thing. It goes way back to you. I mean, I'm sure by now you've heard of Alan Turing. And in the 1930s, Alan Turing was well, as a result of Russell's paradox, which we mentioned last time, which caused problems in the mathematical world. They all of a sudden didn't know if their proofs were really valid because there was this possibility that they had constructed sets like Russell constructed that were paradoxical. And if you use that in your math, then you know you're basically using a contradiction. And if you use a contradiction, you can prove anything. So mathematicians were very concerned. And I said that Hilbert especially was concerned, and he essentially said, look, what we need to do is we need to make essentially it didn't exist in the 1930s, but he wanted to be able to compute everything. And this pretty quickly led to the idea of, well, what can we compute and how can we describe computations? And Alan Turing came up with a model, which is a kind of a state machine model, except the memory is unbounded. So you have this, you have a finite number of states, and you have a finite number of symbols that you can write on a tape, and the tape is infinitely long. And so there's a head that's reading the tape. I bet if I Google Turing machine, we could get a nice diagram, but I won't go that way. So you've got an infinite tape. You've got a head that can read a single cell off the tape. And then depending on what's written in the cell and what state the machine is, the machine can write a new symbol on there and then move left or move right. And so that was Turing's model. That's a Turing machine. And basically, he couldn't find anything that he couldn't write a program to do on a Turing machine. And in fact, you can do things like you can write a Turing machine that will simulate a Turing machine. You can encode a Turing machine, and then you can run a Turing. You write a Turing machine on the tape. That's your start state. You run a Turing machine, and so you could write down an encoding of a Turing machine that's understood by the state part of the machine, and then you could write down the input to that Turing machine, and you could run this Turing machine on that. So then that lets you do kind of meta type things that can get weird, which is how they proved the unsolvability of the halting problem. So Turing developed this model called Turing machines. And then he was British, but he went to do his PhD at Princeton University with Alonzo Church. And Church had developed a system which we talked about in 3015 called the lambda calculus. And it turned out that Church and his students were able to do almost everything with the lambda calculus. And when Turing arrived, he proved the two models of computation are equivalent. Anything that can be computed by a Turing machine can be computed by the lambda calculus and vice versa. So and then they started like trying different models. Well, what if we make the Turing machine have multiple tapes, infinite tapes? Can it do any more? No, it turns out you can't do any more with multiple infinite tapes and multiple heads. And pretty soon it became known as the Church-Turing thesis. It's interesting. In the US, we call it Church's thesis. And in the UK, they call it the Turing-Church thesis. But anyway, the thesis is that anything that can be computed in principle can be computed by a Turing machine. So it turns out any modern computer cannot do anything more than what a Turing machine can do. So it's kind of this amazing kind of like if you take the Venn diagram of like all the things that could be computed and think of those, we don't even know what they are, but there's like a set of them out there in the Platonic universe. And then you take the set of all things that can be computed by lambda calculus, they're identical. Take the set of all things that you could compute by a JavaScript program on a computer with infinite amount of memory, it's the same. So it's pretty astounding. It's Turing complete. And this little language here is Turing complete. So that adds a very long story. But the reason it's Turing complete is essentially the while statement. I mean, that lets you loop. But you might think, okay, but what about a language with a for loop? Well, if your loops are always bounded by a particular integer, then that language is less than Turing complete. So if you've always, used statements that were bounded, the for loops were specifically bounded by an actual integer number, then there's fewer things that you can compute with that than you can with this while language. Okay, so any questions, thoughts? I mean, okay. So, I mean, that's the meaning of Turing complete. I recently started hearing it in the context of people talking about cryptocurrency, because the Ethereum programming language is Turing complete. Suddenly people who have no idea what it means are walking around saying, but the language is Turing complete. It's a very interesting phenomena. So now you know what it means. It means that essentially, so you might go like, this is crazy. How can this be? And for a while, people thought there was a guy at USC who was a computer scientist and a biochemist, and he figured out how to compute with DNA. Like you could encode problems. He actually solved like small cases, like with 4 cities or 3 cities of the traveling salesman problem by encoding the problem in DNA and then somehow or other shaking up this ball of DNA, and then all the recombinations go on between the DNA, and then you can read the answer off the DNA. And for a while, it looked like, well, gosh, maybe you could do something with recombinant DNA. You might be able to compute something that you can't compute with a Turing machine. But then it was shown that no, we can compute everything that you can compute with recombinant DNA with the Turing machine. What about quantum computers? Quantum computers are Turing complete. They can't compute anything that in principle can be computed with a Turing machine. So that's astounding. But what the promise of quantum computers is that for some kinds of problems, they will be able to compute, so much faster than any other model that they could, for example, be used to break all the cryptography used on the web for banks and passwords and everything. So, there is some concern about the fast development of quantum computing, which both the US and the Chinese and the Europeans, everyone's on board trying to get quantum computers to really work. But they're not going to be able to compute anything that in principle. Now you might have to wait, practically, a finite amount of time, but such a large amount of time that, the life of the universe to get the to get the answer out of for some problems. So anyway, that's quantum computing is Turing complete. Nothing new can be computed with a quantum computer. So that's pretty shocking. This little language here is expressive enough to write down everything. Now, there's all kinds of complexity constraints on that. The program that would be able to compute like something that can be computed by a few qubits quantum computer might be so big that we couldn't write it down on all the disks on Earth at this moment. So there's all kinds of complexity constraints here. But in the purely mathematically world, this language is as powerful as any other. So one thing that kind of, is easy to gloss over, and if you take compilers, you go into this in much more detail, but than we will here. But it's a whole language, like almost of the complexity of a programming of programming languages to describe the structure of a language. So, what is a language? Well, I think I have. Let's see, do I have something I can show you? So, what's a language? Has anyone taken 4200 yet? No? Are the people taking 4200 concurrently with us? Only 2. Okay. 4, 5, 6. Okay. So, anyway, the way that we think of languages in a formal sense is a language. So, first of all, you take an alphabet of discrete symbols. Like for us, we're using like the, what is this alphabet called? What's our alphabet? It's not Latin. Somebody help.
Yeah, it is.
It's a Latin alphabet. Okay. So if you take the Latin alphabet and you say, okay, those are the characters, plus maybe the alphabet itself doesn't include a space. Or if you take, like for computer science, we would normally say you take the ASCII characters, the ASCII character set, and we can use those. Now, think about all possible strings that you could, finite strings that you could build with an ASCII character set. Well, let's do it much smaller. Let me go here. I think I fixed, at least, I think this text size is larger on my Emacs. Is it? Okay. Gosh, I would like to put this kind of in a place where I can find it later, but where is that? Oh, it's not there. Okay, so suppose, and usually alphabets are written down like using the character, the capital sigma. And if we say like our alphabet, so this is an alphabet, it's just some set of characters. And let's just say, you know, it turns out that really having just 0 and 1 is enough to describe everything. We know that because we can encode everything we need in Boolean. So now, sigma star is the set of all finite strings, so including the empty string. You've got epsilon in there. You know what? I know I have this written down in a much better way someplace else. Let me just quickly see if I can find it. In fact, I was going to give this to I think I did it in 3015. It's called languages, I think, so I'm not seeing it here. Here we go. All right, these are notes that are intended to explain some of these ideas. So an alphabet is a set of symbols, and we'll go back to the other thing. The problem is that, I mean, I can explain, I can gloss over, and I mean, this is what you is typically done. We can kind of gloss over what's going on here. Let's just gloss over this for just a minute and look at it and see if you can understand what's going on without going into all the details. So maybe that doesn't help, but let's see. So we could say, think about the set of all numerals. Well, what are the set of all numerals? Well, numerals are like numbers, but written down individually, like let's say in base 10. So you get the characters 0 through 10. And then you might want to say, you know what? I mean, you've got two things. What's in a numeral? What if I write down 000? Is that a numeral? Well, you'd have to make up a convention, and you either have to say, okay, look, leading zeros get erased. Oh, and if it's 000, that's the same as zero. But you've got an infinite number of things that are equal there. For every number, you take the number 15. Oh, add a zero. 015. Is that just 15, or do you allow that zero in the front? Maybe in numerals we don't want to allow leading zeros. So it's either just a single zero, or it's a string that starts with the digits 1 through 9, followed by some number of digits 0 through 9. So already we've got like a little language here. The language of numerals is the set of all strings of digits, and either we allow leading zeros or not. Does anyone have a preference? I don't know. In some way, I don't like having leading zeros. That means every time you want to look at a numeral, you have to kind of like pre-process it to delete the leading zeros, and it could be arbitrarily many. So why allow all those useless things in our numerals? So numerals are sequences of digits that only begin with 0 if it is the numeral 0. We're not allowing real numbers here. This is just numerals represent positive integers. Now, once we add minus down here, we'll be able to get, the natural numbers. These are natural numbers. And then down here, when we add minus, we can always get negative numbers by saying 0 minus some positive number. So anyway, whenever you see an n, and where does n occur? N occurs down here. That means it's a numeral. Now, we also have a little language of variables. We have an infinite set of variables. You get to choose what those variables look like. You might want to say, I mean, in the mathematical world, we might say, oh, it's the variable x and y and z and w are variables, and then we'll use x1 and x2 and so forth. But we always need to be able to grab another one. So that's an interesting thing, actually, like the difference between a infinite set, like all the natural numbers, and a potentially infinite set. Like, do you need an infinite number? No, you just need an unbounded number. You don't have to actually go to the limit and get the full infinite set. You just always need to be able to get one more. Okay, so arithmetic expressions are of the form A. And so we're naming this collection of things A expression. Now, this line down here, he's saying that's not going to work. Okay, the way it's structured. This line down here, starting with the A, is telling you how can you construct an A expression. And so let me bring up my Emacs and just make it a little bit smaller. Let me just finish writing this out up here, though. You got 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0. That's in this set of infinite strings over this alphabet, but then we can pare it down. So this is sigma star is the set of all the strings over where sigma is some alphabet. So now here, in this case, what we're going to end up with is trees. because we've got this A1 is an A. That's an arithmetic expression. And this A2 is an A. So if you write down a numeral, that is an A expression. If you write down the name of a variable, that is also an A expression. Now, if you write down A1 plus A2, so what does that mean? Well, A1, normally when you write this kind of thing down, there's an additional stipulation that would say where A1 and A2 are previously constructed A expressions. And what that means is that you have to actually build A1 and build A2 before you can build them, which means we're building from the bottom up. And if we're going to build from the bottom up, then the trees that represent these expressions, the abstract syntax trees that are described by this grammar, are always going to be finite. We don't really want infinitely large programs. Now, you know, it's all been well studied, and sometimes it even kind of makes sense. There's some there's like been deep studies of what if you have logic where you allow infinite sets of formulas, or I'm sorry, infinitely long formulas. What would those logics look like? What if you had programs that were infinitely long? What does that look like? That could be sensible. It can actually be sensible if you're describing like a parallel system where you know, like an operating system where you don't expect the thing ever to terminate. You know, you can sort of build a model where the program transforms itself into a new program, which is what we're going to do in here. This is going to be the basis of our form of semantics. But we're going to always insist that you build A1 first. And if you build A1 first, the two base cases are it has to be a number or it has to be a variable. So you can look at this. Because there's no A's in these first two clauses, you know, those are base cases. But there are A's in all the additional clauses, so those are not base cases. Those are inductive cases or recursive instances of the grammar. So if I write down something like using this grammar, you know, I could say 10, that's a numeral, so that's an A. That has type A. I'll use colon instead of writing in. And X, okay, that's an A. And so now I've got a lot to write, a lot of things. Now I can write 10 plus X, and I can write X plus 10, and I can write, you know, 10 plus 10 and X plus X. These are all, now, in what sense is this, I'm saying everything is a tree. Well, these are the leaves of the tree, and in what sense is this thing a tree? Well, it's a tree because it's really the way to think of this first one. I'll number these. Is that each one of these describes a different syntax tree. Now, okay, so what does one look like? Well, one looks like there's a plus at the root, and then it branches left. Oh, this is so pitiful. And right. And on the left side, over here, I have a 10. And on the right side over here, I have an X. What does the tree 2 look like? Well, it has a plus at the top. And on the left side is an X, and on the right side is a 10. Now, this is like an important thing here, is that you might say to yourself, wait a minute, those are always, if those are programs, X plus 10 or 10 plus X, they're always going to evaluate to the same thing. So they're the same. But if you think about the syntax tree that represents 10 plus X, you know, if you traverse this tree, the left branch is 10. They're obviously not the same tree. They're reflections of one another, but they're different trees. You would never, I don't think you would say that those were the same trees. Would anyone call them the same trees? Now, we could define some kind of equivalence relations on trees where we say, oh, you get to reflect things around and then you get a tree. Okay, but what about A1 times A2? Like if we add that, all of a sudden now, so now I can have like equation 5 or A expression 5 is like 10 times X plus 5. Now, here we start to run into a problem because in and of itself, unless we adopt some kind of conventions, there's actually, this expression could be this tree, or equivalently, I mean, or it would be perfectly reasonable to say, oh, and it could even depend on the kind of parser that you have, what's going to happen here. Oh, I didn't go far enough over. Oh, this is a nightmare. And so this is the 5, and this is the 10, and this is the X. Okay, so now clearly these two trees are definitely not the same. So if I see a linear expression like this with no parentheses, now this one happens, I mean, you could write down parentheses and force, this could be 10 times, and we have the possibility of placing an A expression inside of a parenthesis. So this could be 10 times left paren, I'm sorry, 10 times X in parentheses plus 5. And this one up here would be right? So those are the two different things that happen there. Now, he says that in the book that they're going to just adopt this convention, a few conventions, but one of them is going to be that X plus Y times Z is that multiplication binds tighter than addition does. So this would be the true meaning, according to him, of this linear expression gets interpreted as this, which has this tree representation. Well, I mean, this is a good example of like, you know, what if I mean, I guess I'd be more at a loss to figure out a value for X that wouldn't make this difference. But let's just pick these mean different things. Like we want the syntax to get mapped to a tree, and then when we interpret the abstract syntax tree, the meaning of that abstract syntax tree, we always get the same value. We don't want to have this ambiguity in here. And so he's adopting the convention that multiplication binds tighter than addition, and probably he doesn't tell us what to do with subtraction, but I guess subtraction binds maybe looser than everything. I don't even know. I never know what the conventions are with these. I think this is why a lot of kids are confused in math in grade school. If you write down all the parentheses, there's no confusion. Okay. So now let me just go on to the next slide for a minute so we can look at that, and then maybe we can come back a little bit and look at this description here. I mean, there is a lot of kind of meta information that you need to have to be able to understand in what way this thing describes a language. And so you can think of, I mean, well, let me go over here first for a minute. So, I mean, you can think of, you know, A is the actual, you know, the language of A, of this generated by this grammar is equal to. Now, you have to be careful how you write it down. Like, if I just started writing down all the numerals, I'm going to enumerate all the numerals and I'm never going to get to anything else. So I'll say, I'll write a numeral and then I'll write a variable and then I'll write all the expressions with plus that I can write with what I have so far to the left of the beginning of this thing, you know, 0 plus x and dot, dot, dot. And then I got the time. Now with the times, I've got more because I can use all the, well, I mean, there's only going to be 4 of these. I could write them out, 0 plus x and x plus 0 and x plus x. And now, you know, now I want to do the times, but I could have on the left and right side of times, I could have 2 of these, this and this, you know, all possible combinations of these things here. Like, it's interesting to figure out an algorithm to enumerate all the trees that could be generated by this language so that every tree occurs in some finite position in the enumeration. Like, you don't want like to just start enumerating numerals first, because that's an there's an unbounded number of them. You will never finish writing down all the, you know, 0, 1, 2, 3, 4, 5, 6, 7, 8. You never finish writing down all the numerals. So you have to kind of like, it's called dovetailing. You have to intersperse the different classes here, you know, and then eventually you could put everything that you've got into parentheses, and, you know, and all right. So this is the language of A. It's all possible trees. Now, in this language, but that's a complicated thing right there. This is a pretty complicated structure, because there's recursion involved in the description. Now, B, I'll just say about B's first. B's are Boolean expressions. So you could check whether 2 arithmetic expressions are equal, or except that you can, so like there's two levels. One is what can you do in the programming language, and the other is what are the trees of B. And the trees of B are constructed by taking any previously constructed arithmetic expression and then putting it as the left subchild of a tree whose root is the equal sign, and then putting to the right subtree any other arithmetic expression. And all of those are Boolean expressions. It's kind of interesting that there's no true or false or not, there's no constants in this thing. But I mean, you could adopt a convention and say that, okay, when I'm going to write 0 equals 1 for false, and I'm going to write 0 equals 0 for true. And now you could say, okay, those are abbreviations for true and false. And you could plug them in any place you needed to write down a true. All right, I'm not getting any, I'm feeling all alone here. Any questions? Come on.
None here.
I don't know. Okay. Maybe it is pretty simple, and maybe it is pretty intuitive at this point, but I'll tell you that a lot of students get confused on this later when, about it. All right, let's just look really quickly at the languages in the statement language, which are the actual programs, right? These are just Boolean expressions. These are the constructs in the programming language. So you can take a variable and you can assign the value. I mean, from the semantic point of view, if you were going to evaluate A, get back a number, store it in the location referred to by the variable X. But as a syntax tree, you just got a colon equals is the root. And on the left side, you have the name of the variable. And on the right-hand side, you have an arbitrary arithmetic expression, some arbitrary, any element of this language can be put on the right-hand side as the right subtree of a colon equals assignment statement. Skip is just a constant. So you'll notice that this one contains no S's, and this one contains no S's. So those two are always going to be the things at the leaves of any tree that you can construct here. Well, except you could also have a Boolean expression because it's the left leaf, and now these contain no S's. So the leaves of your tree are either going to be an assignment, a skip, or a Boolean expression. S1, S2 means evaluate the program S1, or the statement S1 first. And then after that's done, evaluate the statement S2. So, this semicolon is a sequencing operator in the programming language. So, if I write skip semicolon X gets the value of 2, that's a program, and that's a statement in this programming language. Now, it turns out that skip is a no-op. It doesn't change the state of memory in any way. So, you know, one thing we're going to be able to prove is stuff like, oh, skip is the same program, followed by x gets a value of 2, is the same program as x gets a value of 2. So what if I want to write down the tree for this one here? The tree for this looks like what? Well, it's got a semicolon at the root, and then the semicolon has two things under it, and on the left side is a skip, and on the right side is a colon equals, and then on the left side of that, that has a left and right side, and on the left side of that is an X. The right side of that is a 2. So that's the abstract syntax tree that reflects the structure of this linear sequence of characters. So now in the compiler class, just, you know, if you take compilers, you spend about half the class, half the semester, working on ways to translate linear sequences of characters into the abstract syntax trees. And then the second half, and actually I think, you know, and that's called parsing, the building of the abstract syntax tree. So like a, and if you took not discrete math, if you took functional programming, we worked with parsers to create the abstract syntax trees. And then you can do what you want. It's much easier to do things with an abstract syntax tree because you've got a tree data structure. So if you want to find out certain things about the tree, you just traverse the tree. If this linear thing, I mean, I could put quotes around this, right, to indicate that, okay, this is a string. Or it's even worse. It's something like, it's like a list of, you know, individual characters. Right? But if that's my program, this is my tree. The process of generating the tree from the program is called parsing. And it's kind of complicated. And you'll need to do it. So, I mean, you know, in virtually any programming job anyway that you go into, you at some point are going to have to take stuff and build a data structure out of a string of characters. And so in some, you know, you might not be parsing and building an abstract syntax tree for a real full-blown programming language, but you might be doing it for a small language. Questions? Such a quiet bunch. Maybe is this, well, all right. I'm not going to worry if I'm making it too easy. All right. So let's look at the arithmetic expressions. And the Haskell representation of arithmetic expressions is very much, oh, I flipped the num and int on this, but okay, is very much like the actual representation of arithmetic expressions. Instead of but you have to use a constructor for the data types. We have to signal kind of like, you can think of, remember that, oh gosh, let me try and find, here's a real Haskell code that builds this data type. Hopefully this works. Because I just upgraded my Ubuntu to 20, whatever it is, from 18 to 20, and man, it took forever to get things sorted out. But okay, so now in this previous version, like we looked at, let's look at like 10 times x plus 5. And now let's write that down. And it turns out we can write both of these trees down in a linear form that is unambiguous. So if I want the top one, I got to say mult. And the first thing then is a num, and it's 10. And then the left branch, or I'm sorry, the right branch then is a plus. And then it has an A expression under it, which is, I think I just used V. Yeah, V. X is, so now I'm using the constructor V to make a variable. Here's my variables up here. In the mathematical notation, they're just written down like X. Here, I got to be more specific. I'm saying, okay, I'm going to represent variables as strings, but the V is going to be the constructor that maps a string and makes it an A expression. So now this is an A expression, and on the other side of plus, I need another A expression, and there I can use num 10. And so what happens, Haskell says, like if I ask Haskell, what's the type of that thing? It says, oh, that's an A expression. Can everyone see that? So here's the a linear representation. But if we wanted this one, we can write it like that. Now, the only reason this A paren is in here is to kind of more closely match his syntax, but we don't actually we never need to write down parens, because I can write the other tree in Haskell by writing plus num 10 times, or mult, I'm sorry, I want to do the mult 10 plus, so I'm doing this one, right? Oh no, the first one was the top, then I'm doing a plus, the left subtree is a mult, of 10 and var x, and the right branch is just the number 5. So all of a sudden I'm seeing that it looks like I didn't do this right, because I didn't put the 5 in. I put the 10 in both places. So I'll do that, and then I'll show you the previous one. This one should be num5. And they're both A expressions. So Haskell has made it extremely easy because this thing here completely describes the abstract syntax trees for the A expressions. It's a very little bit of code. Now, you may forget that, like, what's the type of, for example, V? V takes a string and returns an A expression. So V is a constructor that you give it a string and it gives you back an A expression. So now you can use it, you know, in the mathematical presentation up here, wherever there's an A1 or an A2 or an A. And that's how you get a variable. That's a variable. Questions? No. How are we doing on time? Uh-oh. It looks like I got 17 chats or something. Oh, for some reason, the chat doesn't. Ah, there's no division in A. $4,200 is not complexity. Well, I guess he does. What do they call it? What is 4,200? It's something like it's not just complexity theory, but that is part of it. Somehow I don't see the chats do not show up when I'm sharing my screen. What a bummer. Computability and complexity, right? So you cover, probably you cover Turing machines in there. John Cowles used to teach that class for years and years and years. He just wouldn't give it up. And he didn't like Turing machines, so he actually taught everything with this little while language as the language for that, for, you know, Turing, as a Turing complete language. Okay, so I don't know, for some reason my LaTeX, I cannot figure it out. Like, this is why I'm like sweating bullets. Whoop, just before the class. Oh, now what did I do? I completely closed it. I couldn't fix that. Okay, so what are the kinds of things? Let's look. I'm going to show you down in this file, which is probably not, you know, like, this is, if you look forward, and I'm skipping over transitions right now, transition systems here right now, like the actual mathematical description of transition systems. But this thing, big step A prime here, gives you a semantic evaluator for these things. Now, the way the rules are written down, it would be like, okay, A1 arrow V1 and A2, I'm writing down the mathematical looking rule for the big A step prime function on this one. And then you would say A1 plus A2 evaluates to V1 plus V2. So mathematically, this is how this would be displayed in the book. Oh, it's not even that, right? He does this. I'm not sure why, but it could just be a convention. And then it would say here where V is equal to V1 plus V2. And maybe the thing to note here is that this would be, in our notation, the would really look like this. And this plus, so this plus here is the syntactic plus. And I guess that's why they write it to the side of the rule. That's the real mathematical plus. So maybe to make this look like more like the actual rule in the book, which is on page 33, if you have the book, I could say V1 plus V2. And then here I could just say it's V. So that's the rule for evaluating plus. Evaluate the left subtree all the way to a value. Evaluate the right subtree all the way to a value, and then add those two values together, and that's the answer. So if I split this window again, and now, one thing to note, though, is that the reason this is big step A prime is because there's no variables here. He says somewhere in the book, and it's a little bit confusing, he said, first of all, the table 3.2 is labeled big step translation rules for A expressions. But somewhere in the text, it says, oh, for now, we're disregarding variables. Now, if we were sitting in class, I'd say, like near the top of my list of students here, I don't know. All right, I'll scroll down. That's not fair. I'd say to Noah Fulton. Noah, what's the value of x plus 10? I see. Are you there? Oh, good. He is. I thought, yeah,
I'm trying to read it, but I'm trying to find what the initial value of x was.
All right. Yeah, right. So that's your answer is you don't know because you don't know what x is. So the point, when I do that, like students, like will freak out. What? I don't know what x plus 10 is. But, there's a simple answer and there's a perfectly good reason you don't know what x plus 10 is. And the reason you don't know what x plus 10 is because you don't know what x is. So when we want to do the semantics that includes variables, and I think I have it below, maybe. No, I formalized derivations and then proofs, but okay. Is because you need more information. You need something that's typically called an assignment or an environment that says the value, it's a function, you give it an x, or you can think of it as like a map. You give it an x, and it returns you the value of that x. So let's look over here at like, well, first we can do, so I'm going to have to change these variables to make this darn thing work. All right. Okay, so that's just the term. And now I can say big step A applied to this. And it says 115. Now, what was the other one? That's the one with plus in the front. Here's the one with mult in the front. And I need to change this to num11. And that gives you different answers. So you get different values back depending on which of those two expressions you evaluate. But this is an evaluator that is stepping through, and the first thing it does, it says recursively evaluate num10. So, but what is the big step evaluation of a num is just return the number. So like if I say big step, whoops, not there, down below. Big step A prime num10, well, you get back what you expect, 10. On the right-hand side, I've got I've got mult 10 and 11. Oops, final paren missing. Okay, that gives 110, 10 times 11. And then, so that's the left branch, and then the right branch was actually num15 or num5. And so this all gets recursively constructed by this little program. So the first thing it sees is the plus, and so it comes down through here and gets to the plus row, and it says, okay, evaluate the left branch of the plus, and the left branch of the plus is multiply 10 times 11. And so we recursively do that, and V1 gets the value of 111, right? What is it? 10 times 11, 110. And then it says on the right branch, evaluate 5. And so then this gets 5. And then you evaluate, use ordinary addition to get back 115. That makes sense? Now, this, in a way, is a bit simpler, this style here of writing this down. So like, here's the rule. This rule simply says for numbers, simply says, n, whoops, he uses a lowercase n, evaluates to v, and then he says if, and then he writes all kind of fancy scripty stuff. This is like a scriggly, fancy scripty n, and then he has like this Scott brackets applied to n, and he says, okay, that's equal to v. And all this is convert the numeral, which is a sequence of digits, into v. Now, we did something really to simplify that. We don't really have numerals. What we have are Haskell numbers. So somebody asked about division, and we could write a program using the while loop. That would be like a good little exercise to try to do, is to write a little division program that, let's say starts with, by the time we get to the real semantics, the kind of like the A expressions having variables and B expressions, and I don't know, maybe we don't see the B expression stuff before the page I asked you to read to. doesn't. You have to get to a little bit further along than where I asked you to read to see the the Boolean expression stuff. And then by the time we get there and we get to he waits till the next chapter to do the statements. So, okay. Any thoughts, questions? Not a thing. Oh, 2 chats. Okay, somebody's trying to have after sharing screen. Double click the top of your Zoom to be able to see chat participants. Okay. Bye.
Bye.